So, good afternoon, students. This is Arvind, Assistant Professor, Department of EEE, DBS IT Kavali. So, in the previous class, I discussed about some lost concepts like different types of generators like series shunt compound generators. Okay, and now I am going to discuss the third chapter. I am going to start the third chapter, that is DC motors. Okay. So actually in the last chapter we discussed about the DC generators, and now in this class I am going to discuss DC motors. Okay. So you already know the definition of DC generator. So the DC generator is a machine which converts mechanical energy into electrical energy. It's similar to this, but in a DC generator, in a DC motor, the mechanical energy is the electrical energy is converted into mechanical energy. Okay, the DC motor is a device which converts electrical energy into mechanical energy. So the energy conversion process is quite opposite to that of the DC generator. Okay, so actually in a DC generator, the input, that is the mechanical energy, is given by the prime mover. Okay, but while in a DC motor, the input is a mechanical the input is electrical energy, okay, which is given by the DC supply. Okay, so now I'm going to start the DC motor. So before going to the topics, firstly I will give the syllabus of the total contents in the third chapter, that is introduction, and next force and conductor carrying current, and operating principle, and back EMF, torque and power developed by the armature, speed control of DC motors. We have different methods to control the speed of the DC motor, that is armature control and flux control methods, and the necessity of starters, and constructional details of 3-point and 4-point starters, and characteristics of DC motors, and next losses in a DC machine and condition for maximum efficiency, and then testing of DC machines. We have different types of testings available in for the DC machine: brake test, Swinburne's test, Hopkinson's test, Field's test, retardation test. Like this, we have to cover these topics in coming classes also. And now I'm starting with the introduction part. Okay, so introduction. So basically, I'm discussing about the DC motor. So that's why I'm starting with the DC motor definition. Okay, DC motor is a machine which converts electrical energy into mechanical energy. So these motors are used in steel plants, paper mills, textile mills, cranes, printing presses, electrical locomotives, etc. So this is the diagrammatic representation of conversion, energy conversion process in a DC motor. Firstly, we will give electrical energy as an input to the DC motor, and the DC motor converts this electrical energy into mechanical energy. This mechanical energy is also called as torque in this one, torque. Okay, next. So the DC motor works on the principle that when a current carrying conductor is placed in a magnetic field, okay, when a current carrying conductor is placed in a magnetic field, it experiences a force. It experiences a force. So the direction of experienced force is determined by using Fleming's left-hand rule. So in the previous chapter, that is DC generators, um, we discussed about the Fleming's right-hand rule. Okay, that is for a DC generator. And now in this chapter, I am going to discuss Fleming's left-hand rule. Why we are using this Fleming's left-hand rule means to determine the direction of experienced force. To determine the direction of experienced force. Okay, actually the working principle of DC motor is based on the Faraday's law of electromagnetic induction, same as that of the DC generator also. So same working principle used for the same law is used for the used in the DC generator also. Okay, so firstly we will discuss Fleming's left hand rule. Okay, so here place the left hand like this, three fingers, just take three fingers, stretch the three fingers like this. Okay, so this is a thumb, and this is a middle finger, and this is a forefinger. Okay, so this finger is thumb, and this finger is middle finger, and this finger is sorry, This finger is forefinger and this finger is middle finger. Okay. So actually this thumb represents the direction of force. Okay, the direction of force, and this middle finger represents the direction of magnetic field, and this this forefinger represents magnetic direction of magnetic field, and this middle finger represents direction of current. So this is the Fleming's left hand rule. By using this, we have to determine the direction of force. Okay, mainly this one. Okay. So this one is a, in the diagram you will see the conductor placed in this position, in between this. So this is an in conductor. So okay. So this is Fleming's left hand rule. And coming to the main principle of operation of DC motor. So actually the principle of operation of DC motor can be stated in a single statement. So I already said this one in the previous slide. So when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. Okay, the principle of operation of DC motor can be stated in a single statement as when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. Okay, actually in a practical DC motor, field winding produces a required magnetic field. Okay, so while armature conductors plays a role of current carrying conductors only, and hence armature conductors experience a force. Okay, so in a practical DC motor, field winding produces a required magnetic field, and while armature conductors play a role of current carrying conductor only, and hence armature conductors experiences a force. So as conductors placed in slots, okay, as conductors placed in slots which are on the periphery, okay, as conductors placed in slots which are on the periphery, so the individual force experienced by the conductors acts as a twisting or turning force on the armature, which is called a torque. Okay, conductors placed in slots, you already know this one. So which are on the periphery, the individual force experienced by the conductors acts as a twisting or turning force, twisting or turning force on the armature. So this is also known as torque. Okay. Next, so the torque is the product of force and the radius at which this force acts. Okay, the torque is the product of force and the radius at which this force acts. So overall armature experiences a torque and starts rotating. So mainly armature experiences a torque and starts rotating. Okay, next let us study this motoring action in detail. Okay, by using some diagrams, I will explain the principle of operation of DC motor. Okay, so coming to the principle of operation, so consider here I am considering a single conductor. So if you see the diagram, so in between the two poles, that is south and north pole, I am placing one circular shape small hole. So that one is a conductor. Okay, consider a single conductor placed in a magnetic field as shown in the figure. So if you see this figure, you will identify the conductor which is placed in a magnetic field. Okay, magnetic field is nothing but in between the two magnets we are placing the conductor. So it experiences a magnetic field and it produces a main flux. Okay, so that's why I am giving a title as for the diagram conductor in a magnetic field only. Conductor in a magnetic field. Okay, and next, so these vertical lines are the flux lines. So in between the conductor we have four vertical lines. These four are the flux lines. Okay. So next, so the magnetic field is produced by a permanent magnet. So actually the magnetic field is produced by a permanent magnet, but in practical DC motor, it is produced by the field winding. Okay, but in practical DC motor, it is produced by the field winding when it carries a current. When it carries a current. Now this conductor is excited by a separate supply. Okay, now this conductor is excited by a separate supply so that it carries a current in particular direction. Okay, so next we will consider another diagram. So it shows that it carries a current away from an observer as shown in the figure. So like this. So this is the diagram. So here in this one, the flux produced by current carrying conductor. So that the circular shape in between the two poles, south and north pole, we are placing one conductor. So in this case, that conductor carrying a current, okay, and it produces a flux. It produced a flux. It produced a flux. It produced a flux. Okay. Next, so any current carrying conductor produces its own magnetic field. That means flux. Okay, any current carrying conductor produces its own magnetic field around it. That means in circle. Around it means in circle. Okay, if you see this diagram, you will understand. So there is a conductor placed as a some hole and a plus mark is there. That is the current carrying conductor, and around the conductor we have some circles. Those are the flux lines. These flux lines is produced by the conductor only, current carrying conductor only. Okay. So any current carrying conductor produces its own magnetic field around it. Hence this conductor also produces its own flux. That means in the before figure around. So the direction of this flux can be determined by right hand thumb rule. So in the DC generator also we used this one. By using the right hand thumb rule, we are finding the direction of the flux. And in this case, in the DC motor, we are using the Fleming's left hand rule. So by using that left hand rule, we have to determine the direction of magnetic field. So in the right hand rule, we have to determine the direction of the flux. Okay. And in this one, for the direction of current considered, the direction of flux around a conductor is clockwise. That means in this way it will act, it will rotate in a clockwise direction. So for direction of current considered, the direction of flux around a conductor is clockwise, not anti-clockwise. It is clockwise. And for simplicity of understanding, the main flux produced by the permanent magnet is not shown in the figure. So in this one, we are not showing that one, that is the flux, main flux. We are just showing the flux by the conductor and current carrying conductor only in between the two poles. But I am in the diagram, I am not showing the main flux. Okay, for simplicity of understanding. Okay, next. So now there are two fluxes present. Now there are two fluxes present. That is the flux produced by the permanent magnet. It is not shown. Okay, the flux produced by the permanent magnet, that is called main flux. It is not shown in the diagram. Okay, and the flux produced by the current carrying conductor, it shows. It is already shown in the diagram. Okay, the flux produced by the current carrying conductor. So these are shown in the below figure. So if you see this diagram, so we are using two poles. One is south and one is north pole. In between, we are placing a current carrying conductor, and it consists of two fluxes. One is main flux and another one is current carrying conductor produced flux. Okay. So in this case, what happens means, so from this it is clear that on one side of the conductor, both the fluxes are in the same direction. Okay, from this it is clear that on one side of the conductor, both fluxes are in the same direction. So in this case, on the left side of the conductor, okay, on the left side. So if you see this diagram, so on the left side, what will happen? The fluxes are helping each other. The flux lines of the two fluxes help each other. So on the left of the conductor, there is gathering of the flux lines as two fluxes help each other. So as against this, on the right of the conductor, the two fluxes are in the opposite direction and hence try to cancel each other. So if you see the diagram, on the left hand side, the flux lines are helping, gathering each other, are helping each other. That means addition of fluxes. On the right hand side of this diagram, the two fluxes are cancelling each other. The two fluxes are cancelling each other. Okay, so due to this, the density of the flux lines in this area gets weakened. Okay, due to this, the density of the flux lines in this area gets weak. Okay, and next, so on the left, that means here. So if you see this diagram, you will understand. So here on the left side, there exits high flux density area, while on the right side of the conductor, there exits a low flux density area. Why? So by adding the flux, we have the high density area, high flux density area. But in the right hand side, we are cancelling the fluxes. Okay, that means there is a low, it is a low flux density area. Okay, so that's why I am telling the point, that is, so on the left there exits high flux density area, while on the right of the conductor there exits low flux density area. So if you see this diagram, the direction of force is like this. So that circle and into mark is there, that is a current carrying conductor, and it experiences a force. That force is in the direction like this. Okay, so one is weakening flux and another one is strengthening flux. Okay, in the left hand side we have the strengthening of flux. Why? Because in that side the fluxes are gathering. On the right side the fluxes are cancelling each other. That's why on that on the right side we have the weakening of flux. Okay. Next, so this flux distribution around the conductor acts like a stretched rubber. So stretched rubber under tension. Okay, so this exerts a mechanical force on the conductor. That means when we stretched and released the rubber, what happened? It will forcefully, it touches our finger. Okay, when we place a rubber in between the fingers, so when we stretched the rubber and released that one, what we experienced? It touches as a force, it touches as a force to the finger. Okay, like this. So this exerts a mechanical force on the conductor which acts from high flux density area towards the low flux density area. Okay, that is from left to right. So on the left side we have the high flux density area, on the right side we have the low flux density area. So it travels the mechanical force on the conductor which acts from high flux density area to low flux density area, that is from left to right, for the case considered as shown in the figure, like in the previous figure. So this figure gives the torque exerted on the armature, that is the mechanical force. I already said this point. So when we stretch a rubber, okay, it will forcibly act on our finger. So we experienced some force, or we experienced some touch like this. So that one is called as mechanical force, and that one is called as a torque also. So the torque exerted on the armature only. The torque is exerted on the armature. So if you see this diagram, you will understand. So these are the three current carrying conductors, and it is on the armature, and these F's are three F's is there. So these are the forces acting on the armature. Forces acting on the armature. Okay. So above one is the field winding. So we have north pole and we have the field winding. Okay. We have the terminals also. Okay. So that is the working principle of DC motor. Okay. That is the working principle of DC motor. And next, coming to the next topic, that is significance of back EMF. So firstly we will see the back EMF, and after that we will significance. So here it is seen in the generating action, that is in the generator. So it is seen in the generating action that when a conductor cuts the lines of flux, so you already know, when a conductor cuts the lines of flux, EMF gets induced in the conductor. EMF gets induced in the conductor. So you have that one question, that is, the question is obvious that in a DC motor, after a motoring action, so after a motoring action means after converting the electrical energy into mechanical energy, so what will happen? So armature starts rotating and armature conductor cuts the main flux. Okay, so is there a generating action existing in a motor? The answer to this question is yes. There exists a generating action in a motor also. Okay, after a motoring action there exists a generating action. That means there is an induced EMF in the rotating armature conductors according to Faraday's law of electromagnetic induction. So according to Faraday's law of electromagnetic induction, we have an induced EMF in the rotating armature conductors. Okay, so this induced EMF in the armature always acts in the opposite direction of the supply voltage. Okay, this induced EMF in the armature always acts in the opposite direction of the supply voltage. So this is according to Lenz's law. So we have one more law, that is Lenz's law. So this law states that the direction of induced EMF, the direction of induced EMF is always opposite to the cause producing it, that is the opposite to the supply voltage. So induced EMF is the cause and induced EMF, sorry, supply voltage is the oppose. Okay. So this is according to the Lenz law, which states that the direction of the induced EMF is always opposite the cause producing it. Opposite the cause producing it. So like this, so in a DC motor, electrical input, that is the supply voltage. So in a DC motor, electrical input, that is the supply voltage, is the cause, and hence induced EMF is the is opposes the supply voltage, is always opposes the supply voltage. That is the statement of Lenz law. Okay. Next, this EMF tries to set up a current through the armature. Okay. So whatever we have the EMF, that is the induced EMF. So this EMF tries to set up a current through the armature, which is in the opposite direction to that. Okay. So which supply voltage is forcing through the conductor? So in which the supply voltage is forcing through the conductor. So as this EMF always opposes the supply voltage. So as this EMF always opposes the supply voltage, it is called back EMF. It is called back EMF, and it is denoted as the letter E suffix B. E suffix B. Though it is denoted as E suffix B, basically it gets generated by the generating action only. Basically it gets generated by the generating action, which we have seen earlier in case of generators also. That is Eg is equal to 5p and Z by 60. We have, you know the formula for the EMF equation. So same here also, only the representation only changed, but the equation is same. Okay, though it is denoted as EB, basically it gets generated by the generating action, which we have seen earlier in case of generators. Okay. Next, so I already said this one, Lenz law. It states that cause opposes the effect. Cause opposes the effect, and that the induced EMF is given as EB is equal to 5p and Z by 60. I already said this one. Cause opposes the effect. Okay. Cause opposes the effect means in this one supply voltage is the cause. Induced EMF is the effect. That means opposes. Induced EMF opposes the supply voltage. Okay, that is the Lenz law. So cause opposes the effect. So here two diagrams is there. One is back EMF in a DC motor. So if you observe the diagram, first A diagram, so it consists of a circular shape and two uh, black shaded ones is there. Those two are the brushes. In that one, in the circle, we have EB with the indication arrow mark in the upward, that is EB, that is the back EMF, and we have the armature current IA and supply voltage V. Okay, so that is the back EMF in a DC motor EB. And next we have another diagram, that is equivalent circuit of the DC motor. So here we have armature resistance RA is in series with the battery or back EMF EB. So that one is indicated with the dotted lines. Okay, here it experiences a armature current IA and it consists of the DC supply or supply voltage V. It consists of supply voltage V. So these are the back EMF. Okay, significance of back EMF. And next coming to the voltage equation. Voltage equation. So in case of generator, generated EMF has to supply armature resistance drop, that is IARA. You know already this one in the generators also. So in case of generator, generated EMF, that is induced EMF, has to supply armature resistance drop, that is IARA, and remaining part is available across the load as a terminal voltage. Okay, and remaining part is available across the load as a terminal voltage. But in case of DC motor, okay, in the previous point I discussed in the case of the DC generator, and here I am explaining the in case of DC motor. Okay, but in case of DC motor, supply voltage V has to overcome back EMF. Supply voltage V has to overcome back EMF, That means EB which is opposing V. So EB is the induced EMF or back EMF is opposing V, that is the supply voltage. Okay, and also various drops as armature resistance drop, that is IARA, brush drop, that is V brush, etc. Okay. Next, in fact, the electrical work done in overcoming the back EMF. Okay, in fact, the electrical work, that is the input for the DC motor. Okay, in fact, the electrical work done in overcoming the back EMF gets converted into mechanical energy. Okay, gets converted into the mechanical energy developed in the armature. So these are all developed in the armature only, not in the field winding. Okay, next. So the voltage equation of a DC motor can be written as V, that is the supply voltage, is equal to EB, that is the back EMF, plus IARA, that is the armature drop, IARA, plus brush drop, that is the V brush. So here, neglecting the brush drop, the generalized voltage equation is V is equal to EB plus IARA. Okay, neglecting the brush drop, the generalized voltage equation is V is equal to EB plus IARA. Why we are neglecting the brush drop means it consists of low resistance value. Okay, negligible value. That's why we are neglecting the voltage brush contact drop in the generator also and in the motor also. Okay, and the back EMF is always less than the supply voltage, that is EB less than V. Okay, the back EMF is always less than supply voltage, but RA is very small, that is the armature resistance is very small, hence under normal running conditions the difference between back EMF and supply voltage is very small. Okay, under normal running conditions the difference between back EMF and supply voltage is very small. Okay, next. So the net voltage across the armature is the difference between the supply voltage and back EMF. Okay, the net voltage across the armature, that is VT or V, is the difference between the supply voltage and back EMF, that is V minus EB. Okay, supply voltage means V, back EMF means EB. The difference between supply voltage and back EMF is the net voltage. So which decides the armature current? That decides the armature current. Hence from the voltage equation we can write IA is equal to V minus EB by RA. That is armature current IA is equal to V minus EB by RA. So this is the armature current equation. IA is equal to V minus EB by RA. And next, power equation. So here the voltage equation of a DC motor is given by V is equal to EB plus IARA. So you know already V is equal to EB plus IARA, and multiplying both sides of the above equation by IA. So multiplying both sides of the above equation by IA. So from this we can get V into IA, that is equal to EB into IA plus IA square RA. By multiplying with IA on both sides of the above equation, that is the voltage equation of a DC motor, we will get this one, that is V into IA. So that is equal to EB into IA plus IA square RA. So this equation is called power equation of a DC motor. Okay, so thank you. So up to now I am discussed about introduction to the DC motor, and next I am discussed about Fleming's left hand rule, and then I discussed about principle of operation of DC motor, and then I discussed about significance of back EMF, and next voltage equation and power equations of a DC motor, and armature current also. And in the next class I am going to discuss torque equation of a DC motor. So that is a very important topic in this one, that is torque equation of DC motor. But actually I forget to tell that the construction details of a DC machine, whether it is a DC motor or a DC generator, the construction details is same for both. that is DC motor and DC generator. Okay, thank you.